Hi friends, welcome back on our YouTube channel. In today statistical mechanics, we are going to discuss about chemical potential. So let's start chemical potential. In the current lecture, we will discuss about chemical potential in thermodynamics. Chemical potential of an ideal gas, conservation of particle number, and also about chemical equilibrium. So these four topics we will cover in our current lecture. So first of all, chemical potential. Chemical potential in thermodynamics. In thermodynamics, mu, that is chemical potential, is defined by the change in Helmholtz free energy A as dA equal to minus P dV minus S dt plus mu dN. Here T is temperature, V is volume, P is pressure, and N is particle number. Here dN is the change in N at constant volume and constant temperature. Since A equal to U minus Ts, here S is entropy and U is internal energy. So if we differentiate this equation, then dA equal to du minus Tds minus S dt, and from here du equal to dA plus Tds plus S dt. Now dA is this one, so we replace this dA by this value. So du equal to minus P dV minus S dt plus mu dN plus Tds plus S dt. Now S dt and S dt will be cancelled out. So du equal to minus P dV plus Tds plus mu dN. And this is actually more general form of first law of thermodynamics. So this is the more general form of first law of thermodynamics. Gibbs free energy G is equal to A plus PV. Now if we differentiate this equation, then dG equal to dA plus PdV plus V dP, and since dA equal to minus PdV minus S dt plus mu dN, so if we replace this dA by this value, then dG equal to minus PdV minus S dt plus mu dN plus PdV plus V dP. Now PdV and PdV will be cancelled out, so dG equal to V dP minus S dt plus mu dN. And from here mu equal to dG upon dN at constant pressure and constant temperature. So if pressure is constant, temperature is constant, then dP and dt will be 0. So dG equal to mu dN, or mu equal to del G upon del N at constant pressure and temperature. And from this equation, if volume is constant, then this will be 0. Temperature is constant, then this is 0. So dA equal to mu dN, or mu equal to del A upon del N at constant volume and temperature. Since du equal to minus PdV plus Tds plus mu dN, and from here if we find the value of mu, then if V is constant, then dV equal to 0, entropy is constant, then ds equal to 0. So du equal to mu dN, and from here mu equal to del U by del N at constant volume and constant entropy. So mu equal to del U by del N at constant volume and now if we compare these two equations, then del A by del N at constant V and T is equal to del G upon del N at constant pressure and temperature, which is written here. And this is Maxwell relation. So this equation gives the value of chemical potential in terms of Gibbs free energy. This gives the value of chemical potential in terms of Helmholtz free energy, and this gives the value of chemical potential in terms of internal energy, and this is Maxwell relation. Now, chemical potential of an ideal gas. The partition function for ideal gas is given by Qn is equal to integration dp dq e raised to power minus beta h divided by h raised to 3n factorial n, and h is here Hamiltonian, which is equal to pi square upon 2m. M is mass and pi is the momentum of ith particle. So if we replace h with sigma I equal to 1 to n pi square upon 2m, then the value of partition function for ideal gas, that is Qn, is equal to 1 upon h raised to 3n factorial n integration dp dq exponential minus beta sigma I equal to 1 to n pi square upon 2m. Here p equal to m into v. M is mass and v is linear velocity. Also, small v equal to capital V upon capital N. If lambda is equal to root 2 pi h cross square upon mkt, then Qn is equal to 1 upon factorial n v upon lambda cube whole power n, and A equal to minus kt log of Qn. Now, if this Qn is replaced with this one, then A equal to minus kt log of 1 upon factorial n v upon lambda cube whole power n. Now, we open it, so A equal to minus kt n log v upon lambda cube minus n log n plus n, because if we open this log, then by using log m upon n equal to log m minus log n, this will be log v by lambda cube whole power n minus log of factorial n, and from Stirling approximation log of factorial n will be n log n minus n, and since here negative sign, so this will be minus n log n plus n, and this will be from log m raised to n log m. So this is equal to n log v upon lambda cube. Now A is this one. So A equal to minus ktn log v by lambda cube minus log n plus 1. So we take n common from here and we get this one. Now we apply log m minus log n here. So A equal to minus ktn log v upon n lambda cube plus 1. Since mu equal to del A upon del N at constant volume and temperature, so if we apply the definition of mu by using this equation, then mu equal to minus kt, and we differentiate n log v upon n lambda cube plus 1 with respect to n. So by using u into v method, first of all log v by n lambda cube plus 1 is constant and differential of n with respect to n is 1. So log v upon n lambda cube plus 1 into 1. Now second time, this is constant, so n as it is. We differentiate log v upon n lambda cube plus 1 with respect to n. So the differential of 1 is 0. Now differential of log x equal to 1 upon x. So the differential of this will be 1 upon V upon n lambda cube. Now we differentiate this. So V upon lambda cube is constant. So V by lambda cube as it is. And differential of 1 upon n is minus 1 upon n square. So on differentiating this with respect to n, we get this equation. Now here V is cancelled with this V. Lambda cube is cancelled with this lambda cube. And n is cancelled with 1n here. So this will be n into minus 1 upon n. And this term remains as it is. Now n and n will be cancelled out. So here we have minus 1. And this minus 1 cancel with this plus 1. So mu equal to minus kt log of V by n lambda cube. If we transfer this negative from here to here, then mu equal to kt log V upon n lambda cube whole power minus 1, or this will be equal to mu equal to kt log of n lambda cube upon V. Since density is small n equal to n by V, so this will be small n, and therefore mu equal to kt log of small n lambda cube. So mu equal to kt log of lambda cube n. So this is the chemical potential for an ideal gas. Now next topic is conservation of particle number. If 1 and 2 refers to particle and antiparticle, then in equilibrium the effective Hamiltonian in the grand canonical ensemble is given by H equal to H1 plus H2 minus mu N1 minus N2. Here 1 stands for particle and 2 stands for antiparticle. According to the conservation for a system, N1 minus N2 is always constant. It means the difference of particle and antiparticle remain always constant. Here N1 is number of particle in a system and N2 is the number of antiparticle in a system. Grand partition function R equal to sigma n equal to 0 to infinitive z raised to n q and vt. Here z is fugacity and n is particle. So if we write grand partition function in terms of particle and antiparticle, then R equal to sigma n1 equal to 0 to infinitive, sigma n2 equal to 0 to infinitive, z raised to n1 q n1, z raised to n2 q n2. Q n1 is the function of v1 and t, and q n2 is the function of v2 and t. Since R is this one, q and vt equal to integration dp dq upon h raised to 3n factorial n exponential minus beta h, and h equal to h1 plus h2 minus mu n1 minus n2. So h is replaced with this one. So this equation will be R equal to sigma n1 equal to 0 to infinitive, sigma n2 equal to 0 to infinitive, z raised to n1, integration dp1 dq1 h raised to 3n1 factorial n1 exponential minus beta h1 into z raised to n2 integration dp2 dq2 upon h raised to 3n2 factorial n2 exponential minus beta h2 into exponential beta mu n1 minus n2. Now this is q n1, this is q n2. So R equal to sigma n1 equal to 0 to infinitive, sigma n2 equal to 0 to infinitive, z raised to n1 q n1, z raised to n2 q n2 exponential beta mu n1 minus n2. But the probability that in a system in the grand canonical ensemble has n particle is W is equal to z raised to n qn is equal to exponential minus beta a, and a is the function of n v t. So The probability that a system in the grand canonical ensemble has n particles is this one. Now R is this one and W is this one. So R equal to sigma n1 equal to 0 to infinitive, sigma n2 equal to 0 to infinitive, exponential beta mu n1 minus n2, and z raised to n qn is equal to exponential minus beta a. So this will be exponential minus beta a n1 plus a n2, or exponential minus beta a n1 exponential minus beta a n2. So we involve exponential minus beta a n1 plus a n2 here. So R equal to sigma n1 equal to 0 to infinitive, sigma n2 equal to 0 to infinitive, exponential beta mu n1 minus n2 minus a n1 plus a n2. Here Qn is partition function and An is Helmholtz free energy corresponding to Qn. It means the Helmholtz free energy corresponding to Qn1 is An1 and the Helmholtz free energy corresponding to Qn2 is An2. In thermodynamic limit, we keep only the largest term in the summed with n1 and n2 determined by del a n1 upon del n1 equal to mu and del a n2 upon del n2 equal to minus mu. Here we calculate A by using relativistic kinematics. Therefore, energy of particle is E equal to mc square plus p square by 2m. So this is the energy of particle by using relativistic kinematics. mc square represents the rest energy or rest mass energy. Therefore, condition of equilibrium will be mu equal to del A upon del n equal to kT log of lambda cube small n, and E is this one. So kT log of lambda cube n1 plus mc square equal to mu and kT log of lambda cube n2 plus mc square equal to minus mu. Here n1 is density of particle and n2 is density of antiparticle. Now, if we add these two equations, then kT log lambda cube n1 plus mc square plus kT log lambda cube n2 plus mc square equal to 0, or kT log of lambda cube n1 plus log of lambda cube n2 plus twice mc square equal to 0. Now, by using log m plus log n equal to log m into n, this will be log of lambda raised to 6 n1 n2. So kT log of lambda raised to 6 n1 n2 plus twice mc square equal to 0. Now from here, kT log of lambda raised to 6 n1 n2 is equal to minus twice mc square. We transfer this kT from here to here. So log of lambda raised to 6 n1 n2 equal to minus twice mc square upon kT. Now we take exponential on other side. So exponential log of lambda raised to 6 n1 n2 equal to lambda raised to 6 n1 n2. So lambda raised to 6 n1 n2 equal to exponential minus 2 mc square upon kT. Because if we take exponential, then e raised to log of lambda raised to 6 n1 n2 is equal to e raised to minus twice mc square upon kT. And exponential and log will be cancelled out. So lambda raised to 6 n1 n2 equal to exponential minus 2 mc square upon kT, which is written here. At temperature 6 into 10 raised to power 9 Kelvin, mc square for electron equal to 200 times mc square of proton. And therefore, e raised to minus 2 mc square upon kT at such high temperature tends to 0. Therefore, N1 or N2 is not essentially 0. So, we ignore antiparticle when kT is very much less than mc square. So, when kT is very much less than mc square, we ignore antiparticle because N1 or N2 is not essentially 0. Now, chemical equilibrium. Consider a chemical reaction in which a group of particles x1, x2 and so on participate and provide a group of particles y1, y2 and so on or vice versa. So a1x1 plus a2x2 gives b1y1 plus b2y2. Here a1 is stoichiometric coefficient. For convenience, x and y are replaced by x and b1 equal to minus a1. So this equation will be sigma I equal to 1 to k a I x I equal to 0. From conservation law, dn1 upon a1 equal to dn2 upon a2 is equal to dnk upon ak. Here dni is the increase in the number of particles of ith type and dni upon ai is independent of I. So dni upon ai is equal to dn, and on cross multiplying this equation, dn1 equal to ai dn. Here I equal to 1 to 3 and so on up to k. Let reaction be at constant V and T. In equilibrium, Helmholtz energy A equal to A minimum. Therefore, any change in Ni from their equilibrium will not change A to first order. So dA equal to 0 or sigma I equal to 1 to k dAi equal to 0 or sigma I equal to 1 to k del Ai upon del Ni dNi equal to 0. Here dNi equal to Ai dN and mu equal to del A upon del N at Vt. So del Ai upon del Ni will be mu I and this will be Ai dN. So sigma I equal to 1 to k mu I Ai dN equal to 0, and since dN is not equal to 0, so sigma I equal to 1 to k mu I Ai equal to 0. Here mu I is the chemical potential of Xi. If the reaction proceeds at constant pressure and temperature, then we use G, that is Gibbs free energy, in place of A. Here we end our session. In today's session, we have discussed about Gibbs potential. Goodbye.